Moving ahead to the common era, what I call the classical period over here, I've highlighted the work of Ptolemy, who lived from 90 to 168 common era. He was Roman citizen living in Alexandria, and he published the Almagest in 150 common era, which was a synthesis of all the prevailing knowledge of the time. Of course, after this period, we saw a decline of classical learning in the Western world for centuries. And we know of the seminal work which were done in different civilizations, including in India. And we also know the growth in Islamic science and some of the words which are in common usage today, such as algebra, algorithm, and star names such as Algol, Aldebaran, goes back to the development and growth of Islamic science. And in about the 11th, 12th, 13th centuries, we saw the establishment of universities and spread of monasticism with the growth of Christianity in Western Europe. Bologna in 1088, Paris in 1150, Oxford in 1167, Cambridge in 1209. And these universities, when it started, were more sort of catered to the priestly class, and it contributed to the spread of monasticism. And they're not the modern universities that you're more familiar with today, but this was the early sort of seeds of universities that grew up in Western Europe. In India, we know of the ancient universities of Takshashila, which from 6th to 5th century, 6th century BC to 5th century Common Era, and Nalanda from 427 to about 1197 or so. And we also know of the seminal contributions of Aryabhatta, 476 to 550 Common Era, who developed an understanding of the eclipses and periodicity of eclipses and various other contributions. I've referred to an article over here by Razaullah Ansari in the Bulletin of the Astronomical Society of India, and who gives a nice sort of summary of some of Aryabhata's contributions. If we come later, then I mentioned about when there was the Dark Ages in in the growth of science in Western Europe, and then we come to the growth of science by Copernicus, Galileo, and others. Copernicus was the one who established the sun is at the center of the planetary system, and they were actually very rooted. Copernicus himself was a priest, and they didn't want to antagonize the church. He didn't publish results for a long time, and you can read much more about him in the web. But I would just highlight two of the books which he wrote. One was a little commentary around 1540 called Commentariolus, and the epic book called De Revolutionibus Orbium Celestium, on the revolution of the heavenly bodies in 1543. And we attribute Nicholas Copernicus to one of the fundamental shifts in our understanding of the universe, in terms of a geocentric universe to a heliocentric one of our planetary system. Galileo, he developed the science of mechanics, movement of bodies, and observations with a telescope. Although lenses were sort of developed in the Netherlands, Galileo really sort of built the telescopes, made astronomical observations, showed it to the community, and he published his results, or summarized the results, in the starry messenger called Sidereus Nuncius in 1610. With his telescopes, he found the moons of Jupiter, which also showed that a motion around the sun was not the only system. And there were other systems which moved around a massive body. Moon was not the only body which showed phases. There were phases of Venus, constellation of Orion. He resolved stars, groups of stars in the Milky Way with the help of his telescope. So you can see that we are coming to not only development of science in terms of establishing the tools, but also trying to do experiments, trying to do observations. Galileo is the one who dropped bodies of different mass from the Tower of Pisa, as reported by a historian who wrote down his biography, and quite different from Aristotle's axiomatic perspective, which suggested that a heavier body should fall faster. But when you actually do experiments, you can show that that is not the case. And you can actually do that experiment at your home. You take a heavy cabbage and a smaller potato, stand up on your table and drop it, and you'll find that they will reach at roughly the same time. If you, however, you drop a feather, it will not, because air resistance will play a much more significant role in that. But within the areas of measurement, you can see that a cabbage and a potato will actually reach at roughly the same time. Tycho Brahe, Kepler, Newton, and Herschel, these were sort of important contributors from about the 16th to the 19th century. Tycho Brahe made very accurate observations of stars. He observed a supernova which went off. We will later see that supernovae goes off at the last stages of the evolution of massive stars. He predates the development of the telescope which Galileo had made, and he made his observatory in an island and was supported by the Danish royalty of the time. Johannes Kepler, you would have read about his laws of planetary motion, which he developed using the data which Tycho Brahe had meticulously gathered. And Johannes Kepler was also deeply religious. Actually, many of these people were. And he saw these laws as more of harmonies of the universe as created by God. And it was left to Isaac Newton, who developed the mathematical tools to understand the motions of heavenly bodies. Many of his results were summarized in Principia Mathematica, which was first published in 1687, and newer editions were published in 1713 and 1726. And Isaac Newton was the one who put forward the universal law of gravitation, which you'd have learned about. And it is a huge step from actually observing, as the story goes, of the apple falling, but to extend this law of gravitation to all celestial bodies, to the furthest reaches of the universe. And although today we have Einstein's theory of gravity, which provides an explanation in terms of understanding motions of celestial bodies, and also particularly in regions of strong gravity. But in a lot of cases where weak gravity phenomena can be understood in terms of weak gravity, Newton's law of universal gravitation and Kepler's laws of motion can be used quite easily without having to invoke the principles of general relativity. Then the example I picked up is William Herschel, who was a refugee musician from Hanover, and he built some of the most powerful telescopes of the time. And he made surveys of the sky. He sketched the structure of the Milky Way from observations of the stars that he observed in our own galaxy. And these seminal contributions led the path to the dawn of a new era in the 20th century. Now let's move on to the beginning of the 20th century. I will highlight a few select developments in the history of astronomy that have made a significant difference to our understanding and to the knowledge that we have about celestial objects. A more detailed outline has been given as an assignment to you, and the choices I've made are obviously a personal one, and different persons may have a different set of choices. The first one that I picked up is the Hertzsprung-Russell diagram. This is the relationship between stellar luminosity and color or temperature, reported initially by Danish engineer and astronomer Enir Hertzsprung in 1905, the same year that Einstein made some of his very significant contributions. And what you can see over here, that a lot of stars lie on one line, which is called a main sequence, when you plot the luminosity of stars against the temperature. And as we learned earlier, the temperature is intimately related to the colors of stars. The massive stars look more bluish, whereas the low mass stars may look more reddish. This was plotted independently by Henry Norris Russell, an American astronomer, in 1914, and at the suggestion of Bengt Stromgren, a Danish astronomer, This relationship is known as the Hertzsprung-Russell diagram. It has played a very important role in understanding the properties of stars and particularly their evolution as they move along different paths in this Hertzsprung-Russell diagram. So this is one of the very significant contributions, because understanding of stars is absolutely fundamental to understanding our universe and all its different constituents. Stars are the ones which make up the galaxies, and units of galaxies make up clusters of galaxies, and they're the basic building blocks of the universe. The next one that I picked up is the period luminosity relationship for Cepheid variable stars. This was found by Henrietta Leavitt. She was working at the Harvard College Observatory and was examining plates of stars in the large and small Magellanic Clouds. And she noted that stars which were brighter appeared to vary on longer time scales. And she noted this in 1908, but published it more formally in 1912. And you can see on the diagram over here that for these classes of stars called the Cepheid variables, the period is closely or tightly correlated with the luminosity. For example, over here, all you need to know is how the intensity of light that you receive from it varies, and it has a pretty regular variation. And from the regular light curve, you can go and determine what its period is. And from the period, you should be able to determine what the luminosity is for these classes of stars called Cepheid variables. Now, at the time that Henrietta Leavitt made this, discovered this relationship, there was no absolute measurements of distances to even large Magellanic Cloud and small Magellanic Cloud. So she actually plotted the apparent brightness of the stars she looked at, but soon the absolute the distances were also measured, and one could measure the intrinsic luminosity, and that provided the calibration for the period luminosity relationship for Cepheid variable stars. But in her case, because all the stars would roughly be at the same distance, the variations within the galaxy would be very small compared to the distance from observations on the Earth to the large or small Magellanic Cloud, that plotting the apparent brightness of the object or apparent magnitude of the object was adequate to establish the period luminosity relationship. This relationship is also extremely important because it enabled us to explore distances beyond what was possible by parallax in those days, and really established the rung of the cosmic distance ladder, an important rung, which enabled us to probe further or measure distances to more distant objects than what was possible with the parallax method at the time. So this was really an important relationship which she found. The other important aspect which I wanted to mention was the discovery of dark matter. Although there were hints earlier, this was usually attributed to Fritz Zwicky, who inferred the existence of dark matter in 1933 while studying the motion of galaxies in a Coma cluster of galaxies. As we mentioned earlier, that galaxies also don't occur in isolation. They're in groups or rich clusters of galaxies where there could be hundreds of thousands of galaxies making up a cluster. And these galaxies within a cluster move around with velocities responding to the cluster potential well. And what Zwicky did was he studied the motion of these galaxies and tried to estimate the mass that would be required to account for the motion of the galaxies. And then he could also estimate the mass by counting the number of galaxies and estimating the masses of individual galaxies. And then he noticed that the amount of mass which was required to understand the motion of galaxies was much, much higher than what you could account for by counting the galaxies which make up the cluster and estimating their total masses. So he referred to this matter which is not observable, but whose gravitational influence one could see in the motions of galaxies at dark matter. This was initially published in German, and today we know that dark matter makes up slightly over about 25% of the universe. So this was a very important discovery as well in the history of astronomy, and it is an important and significant constituent of the universe. one realizes how important this 26% or slightly over 25% is when you realize that all the baryonic matter, the matter that you and I are made of, and all the galaxies and stars make up just about 5% or so of the constituents of the universe. And we're still trying to figure out what the dark matter really is, although there are promising sort of leads, but we're not absolutely certain as yet. Moving on, I would like to highlight two other important discoveries. One is the discovery of quasars. We saw briefly the beginnings of the opening up of the electromagnetic spectrum in the radio region. And when maps are made of the sky, there were regions of radio emission. And the obvious thing was to look for what is the source of this radio emission. And at that time, the most straightforward thing to do was to look for optical counterparts of these radio sources. There were sky surveys at optical wavelengths which had been done, and to find out if any of these objects, or if all of these objects, or some of these objects are associated with optical galaxies or optical objects. And while doing so, you needed actually good positions to be sure that the associations are correct. Otherwise, they could be just chance coincidences. So you needed high resolution observations to be able to do that. And as we shall see, and as you have seen, the resolutions were pretty modest in those days compared to what is possible today. But Cyril Hazard and his collaborators thought of an interesting scheme to find out the accurate position. There was a radio source which was catalogued in a survey at Cambridge, the third Cambridge survey, which was called 3C273. And this particular source was getting occulted by the moon. Now, one knew the position of the moon quite accurately, and using the moon as a diffracting edge, one could also infer the structure of the radio source with high angular resolution than what was possible by other means in those days. And you have to take this, seize this opportunity, because you cannot tell the moon to go here or there. When an occultation happens, you have to seize the opportunity and record your observations. So great care was taken in recording these observations. And then when the accurate position was determined, it was found that there were two components. One was associated with a star-like object, which you can see on the lower middle panel over here. And that was a little strange because stars were generally weak emitters. They were not such strong radio sources as 3C273. But anyway, then Martin Schmidt, what he did was he tried to measure the redshift of the object. By the time one knew about galaxies, one knew about the cosmological expansion of the universe, and so one had to measure the redshift. And galaxies generally had weak emission lines, and they were relatively close by. But when Martin Schmidt took a spectrum, initially there was a struggle to identify the lines, till it occurred to him that they were nothing but the redshifted Balmer lines in the spectrum of 3C273. He estimated a redshift, lambda observed equal to lambda emitted into 1 plus z. Z is a redshift, which is 0.158. And this heralded the discovery of a new class of object, which we call quasars today, that is quasar-stellar radio sources. Further observations with the Hubble Space Telescope in recent times have taught us that these are nothing but galaxies with abnormally luminous nuclei. And the galaxy is not usually observable because of dynamic range limitations. So you need both high angular resolution and high dynamic range to be able to pick out the surrounding galaxy or the fuzz around it, which is a galaxy. So this is another very important discovery because it really opened up the field of studies of active galactic nuclei. And later we learned that these active galactic nuclei often have jets squirting out of them at highly relativistic velocities. And in the wisp which you see, and one of the components which Cyril Hazard determined at that time was radio emission from this highly sort of relativistic jet, which is moving at relativistic speeds, squirting out from the nucleus of the active galaxy. The other class of objects which changed our view of the universe was the discovery of pulsars. Pulsars was discovered by Jocelyn Bell Burnell in 1967 while she was a graduate student at Cambridge working with Anthony Hewish. And what she was studying was the scintillation of stars at radio frequencies. You know the scintillation of stars by the atmosphere, and that is why stars twinkle. They effectively point sources, and refraction in the atmosphere, irregularities in the atmosphere causes the stars to twinkle. What she was looking at were what I would call radio stars now for the time being. They were compact radio sources, which could be outside our galaxy, which are usually outside our galaxy. Most stars are very weak within are weak in the radio region, which are within our galaxy, except some exotic stars. But these compact objects are extragalactic objects, but because they're very compact, they scintillate at radio frequencies due to irregularities in the ionosphere. So she was studying scintillations of radio sources, which was a main project at Cambridge at that point of time. And what she noticed was that there was a particular source, a particular direction in the sky where the signal was periodic. So scintillations is a random phenomenon. So you are not going to see periodicities in the signal. So she noticed that there was a regular periodicity, and that really heralded the discovery of pulsars. So pulsars are basically neutron stars, which form at the end stages of the explosion of massive stars, where the outer layers move out at high velocities and due to a supernova explosion, which takes place, and we see these remnants as supernova remnants, leaving behind a compact objects, which is a highly compressed object consisting largely of neutrons, and it has a very strong magnetic field. It is very high density. It's only about 10 kilometers in size, which is smaller than the city of Pune, say, and is rotating very rapidly. Okay? So because of the strong dipolar magnetic field, emission is emitted along two beams. And when this beam cuts you, you observe a pulse of emission. And they could be extremely rapidly rotating as well. One of the fastest pulsars are the millisecond pulsar. You can listen to this beautiful video, which was made recently by Ben Proudfoot of the New York Times, where Jocelyn Bell Burnell talks about her early career and the struggles that she had to face, not only in getting a science education, but also the discrimination against women that was very widespread at that period of time. So these are a few of the very important discoveries which I wanted to bring to your attention. And as I said earlier, that these are the ones I have chosen. There would be another astronomer who may choose a different set, because there have been many sort of important discoveries which have taken place, both in terms of continuum emission as well as detection of prominent emission lines, which have enhanced our understanding of the universe. Now we move on to some of the important discoveries in astronomy, in the field of cosmology in the 20th century. And again, I will be sketchy and just pick up an example or two. The Hubble Law, which I mentioned about earlier, as something which was based on observations of galaxies, which are moving away. When they move away, their wavelength of emission gets shifted to longer wavelengths. And that is a phenomenon which you would also be familiar with from sound waves. For example, when a train is approaching you, the whistle of a train, compared to when it is going away from you. And Vesto Slipher, working at the Lowell Observatory, found that the spectra of spiral nebulae, these were spiral nebulae or spiral galaxies, were redshifted for almost all. Okay? And redshifted means they were moving away from us. And almost all, because what happens is that when I talk about galaxies, they are actually don't occur in isolation. They occur in groups, and they're moving about randomly due to the gravitational attraction of other galaxies in the group. And some galaxies could actually be approaching us. And that is why you get this negative velocity, or galaxies which are coming towards you, besides galaxies which are moving away from. For example, the Andromeda Nebula or the Andromeda Galaxy, which you can observe with a pair of binoculars on a clear night with good eyes, is a galaxy which is moving towards us. It's a member of our local group, very similar to our own galaxy. But you can see from Slipher's observations that but the bulk of the galaxy, the overriding movement of the galaxy is movement away from us. At the same time that, slightly later, that Georges Lemaitre, based on Einstein's general theory of relativity, he was finding solutions to the equations, and he found that an expanding universe was a solution, and he used existing observations to show that this fitted into the world model of the universe. There's a Russian astrophysicist, Friedman, who had actually also found solutions of Einstein's equations. And he was interested in both expanding and contracting universes, and he found solutions for those. But he was not the one who really linked it up to the observations. So that is why this law, which was earlier known as Hubble's Law, more recently it has been renamed by the International Astronomical Union as the Hubble-Lemaitre Law. And Hubble also found that not only are they moving away from us, but if you can estimate their distances, then the velocity at which they're moving away from us is proportional to the distance. Okay? And this constant of proportionality is the Hubble-Lemaitre constant. Okay? So when a galaxy is further away, then it is moving faster away from us, which means that the wavelength which we observe would be shifted to longer and longer wavelengths. How do we measure the distance? That is something which we will discuss later, measurements of distances of astronomical objects. And for the nearby universe, we can put the velocity as c times the redshift, and the redshift is defined by the observed wavelength is equal to the emitted wavelength, which would be the wavelength in the rest frame, which is the wavelength which you would measure for a particular atom in the laboratory, multiplied by 1 plus z, right? So you can see over here that the larger the redshift of the object, the larger the observed wave, the longer the wavelength it is going to be, right? And larger the redshift, the higher the velocity at which it is moving. Okay? Higher the velocity is moving away, the further away it is, right? So if you can go and calibrate and find out an accurate value of the constant over here, the Hubble constant, then you measure the velocity at which it is moving away from us, you divide it by the Hubble constant, and that will give you the distance to the object. So a lot of effort in astronomy has been spent on trying to determine this Hubble constant accurately, and also see whether that may have evolved with cosmic time. At a later stage, you can perhaps have a look at this annual reviews article, giving it is about 10 years old, but it still gives a nice overview on measurement of this constant, the Hubble constant, which is now known as a Hubble-Lemaitre constant. So we have gone till the early part of the 20th century. What I would like to touch on very briefly is slightly a bit of philosophy as well, and to ask ourselves, is science an endless frontier? Okay. Is there no end to it? Vannevar Bush, who was director of OSRD, which is Office for Scientific Research and Development after the Second World War, he wrote a report to the US President. Eisenhower was the president at that point of time. And in July 1945, titled Science, the Endless Frontier. His object was that science and technology played a major role in the Second World War, and he wanted to ensure funding from it. And one way to ensure the funding was to say that the science is an endless frontier, and you got to keep funding it to push the frontiers further and further. And as we know more, we also often realize that how little we know. Today's model of the universe says that only about 5% is ordinary matter that we see, that makes up all the galaxies that you see, makes you and us, the earth and the moon and the sun, all the stars. All that consists of just 5% or so, which is referred to as baryonic matter. Nearly about 27% is dark matter, which we know exists because of its gravitational influence. And we'll look at this a little bit in more detail later. And we have some intelligent guesses on what it might be, but we don't have any conclusive answers. And we know even less of what this component called dark energy is, which is responsible for the accelerated expansion of the universe in more recent times during the course of evolution of the universe. So you can see that how little we know of what makes up our universe. And if you look at the history of science, you will find that instances of examples in all disciplines of how little we know when whole new areas were opened up, which we were not aware of. As students of physics or as students of astronomy and astrophysics, let me just give you one example drawing from astronomy and astrophysics, just to illustrate that even the best of us can be wrong. And that is also a lesson that for you as students, that you must never shy away from querying and asking questions. Albert Michelson, you would have heard about the Michelson-Morley experiment, measuring the velocity of light, doing away the theory of ether. It is said that he sort of said that the grand underlying principles have been firmly established. This was in the 1890s. Lord Kelvin, whose contributions to thermodynamics and areas of physics are fundamental, he's also reported to have said in the 1890s that the future truths of physical science are to be looked for in the sixth place of decimals, indicating that all the fundamental laws and rules of physics have been established. So all we need now is accuracy. And how wrong could they have been? It was only a little later that we found, an early part of the 20th century, late 19th century, came Henry Becquerel, discovery of radioactivity, Rontgen's discovery of X-rays, discovery of radioactivity and extraction of radium by Marie Curie. We had Einstein's general theory of relativity and special theory of relativity, Max Planck's concept of the quanta, Ernest Rutherford's model of the atom, Schrödinger's development of wave mechanics, quantum mechanics, Heisenberg's uncertainty principle, and the list can go on and on. And I just talked about physics and astronomy, astrophysics. So you'll find examples of this in biological sciences and other sciences as well. When we talk about the development of science, you can also see how technology has played a very important role. It is not just that applied science or fundamental science leads to understandings of fundamental science without linkages from technology or applied sciences. These are all closely linked together. Governments are extremely short-sighted when they don't fund fundamental science and overstress the importance of just applied science or technology, because it is these two which drive one another. And you can see this in examples as we go through this course on the advances which have been made. The big questions of the day today are probably the origin of the universe, formation of planetary systems, the origin of life itself. To pick on recent examples, I just picked up the Nobel Prizes in Physics in 2019, which were given to James Peeble from Princeton University, USA, and Michel Mayor from the University of Geneva, Switzerland, and Didier Queloz from the University of Geneva, Geneva and the University of Cambridge. And the Nobel Prize for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos. To try and infer the existence of the exoplanet not only required a telescope, but a technology to make the very accurate measurements that were required to arrive at that conclusion. Jim People laid the foundations for the theoretical discoveries in theoretical cosmology. But cosmology too has been a largely observational driven science in recent modern times. The discovery of the cosmic microwave background temperature, radiation, with a very accurate temperature of about 2.725 or 2.73 degrees Kelvin, is perhaps the best example of black body radiation that we know of. And this provided firm evidence of a Big Bang kind of origin of the universe, which had a very sort of hot or fiery past. And small fluctuations in these, which have been later measured, were only possible with the development of technology. And these small fluctuations hold a key to the formations of structures, formations of galaxies, in one of which we reside today. This was the contributions of what I talked about were Peebles and many others, which, and the observational side were led by many. And in this slide, what I've shown is the contributions of Michel Mayor and Didier Queloz for the discovery of an exoplanet orbiting a solar type star. And this solar type star led to their initial work led to missions and increased efforts of trying to find extrasolar planets. And today we have over 4,000 of them, many which are similar to the Earth and are potential places where life could exist, although there is no evidence today of life existing anywhere else, but it's probably only a matter of discovery, not a matter of non-existence. And we also have been enriched by the discovery of exoplanets, because if you look at our own planetary system, which we will devote to at some point later in the course, that it consists of the rocky planets closer to the sun and the gaseous planets further away. But you find all kinds of different situations over here. You find gaseous planets which are quite close by as well. And so it has really enriched our understanding of the formation of planetary systems, their evolution, and the different kinds of scenarios in which they may occur. Now, tracing the history of the development of astronomy as a discipline, astronomy as a science, from millennia ago, thousands of years ago, to more modern times, we have talked about the different ways or instances of where scientific discovery is made, or science has progressed. And two of the very eminent names which you will come across when you look at the philosophy of science are Karl Popper and Thomas Kuhn. Karl Popper, his book is rather terse to read, The Logic of Scientific Discovery, but what he basically said was science progresses by falsification. For example, if Einstein's theory predicted that the ray of light should bend by so many arc minutes or arc seconds, and it did not, then you would actually say that theory is not correct. So it is through falsification that you try and pick out what is correct. Thomas Kuhn, on the other hand, said that the structure of scientific revolutions, which he published in 1962, the science enjoys periods of relative stable growth punctuated by revisionary revolutions. For example, our Copernican revolution, Copernican shift from a geocentric to a heliocentric universe would have been a major shift in our understanding. But I think although, if you read the literature, you'll find that these two are often posited or put one against the other, science progresses probably by both. because scientific revolutions often don't happen in vacuum, and it is the men and women of science who keep pushing the frontiers, come up with inconsistencies which you try to understand or explain, that you develop sort of major shifts which might be called revolutions. And also one may note that when we look at astronomy in greater detail or look at objects in greater detail, that you may develop a certain framework or understanding of it. Astronomy as a discipline is not like physics, where you can sit down and tune your experiments and make measurements. You observe the universe, you make your measurements, and you make certain predictions of and see whether that holds up. For example, you may find a certain relationship between two parameters. Maybe it's a luminosity and a mass. But you may also find that most of the objects follow the relationship, but there may be some or a few which don't. That doesn't mean that you junk the paradigm which you have developed, but you try and develop a deeper understanding of why these deviations may occur. So the growth and development of our understanding of science is many faceted. And as you sort of develop a deeper understanding of astronomy and astrophysics, you should be able to relate to some of the philosophical developments as well as historical developments that we talked about today. So I'll end the first part of today's sort of discussion with a quote from Michael Faraday, that as men and women of science, we are often our own best critics. And that is something which you have to learn in terms of your own understanding as students and researchers of science as well. That it's only by querying and questioning that you develop a deeper understanding. And it's only by critiquing what you are developing thoroughly that you develop new ideas and thoughts. Michael Faraday said, the world little knows how many of the thoughts and theories which are passed through the mind of a scientific investigator have been crushed in silence and secrecy by his own severe criticism and adverse examination. This is from a quote by Carl Pearson in Grammar of Science. Okay. So I've tried to give you a brief overview of the growth of astronomy, a historical perspective from ancient times to modern times, just cherry picking a few of the seminal developments. Somebody else may choose some other sort of seminal points, but this basic idea is just to give you an idea of the growth of astronomy and astrophysics, and to also to make you realize that you as students of physics are a part of this long journey to develop a deeper understanding, and some of you will hopefully, take on, research in astronomy and astrophysics and help further push the frontiers of our understanding.